Hello everyone. We are Krzysztof Kudryński and Błażej Kubiak, and we are going to talk about deep learning in computer vision. And the plan for our talk is first to get extremely excited. And we are dedicating 7 minutes especially for that, because the emerging technologies just deserve that. Within the next 18 minutes, we will try to truly understand the concept of convolutional neural network by developing a short TensorFlow project. And for the rest of our talk, we will walk through a very challenging real-life application of CNN in our own computer vision project. When we finally understand and apply these technologies, the last minute we plan to devote to being scared about the possibilities of these technologies in the future. So, let's start by talking about science fiction. A classic from 1982, in this scene, Harrison Ford is analyzing a photo using a hyper-mega computer. It is a year 2019, so it can obviously zoom and enhance beyond any physical reason, but that's not the end. This computer can even look around the corner. What a technology. Now, this film is a classic, it's great to watch, but although the film was shot when I was still very young, but even then, I could feel something was not right. And I'm sure that everyone here who watched it felt this strange embarrassment on this scene. If you did, you should know about this, that while we still haven't reached 2019 yet, the world of science already says we are actually able to reconstruct details that seemingly could not have been captured by the camera due to its physical limitations. But well, okay, we can believe in zoom and enhance, but looking around the corner, well, the end of 2017, guys from MIT and Google published a method in which using a camera, you can actually trace objects around corners by looking at indirect reflections and what is going on with the light. Well, and it's quite amazing because it can do it with such a precision. The trace you can follow up to centimeter level while the guy is behind the corner. Well, you cannot look at the face of the lady android from the film, but it's not 2019 yet. And this technology was developed by people from blood and bones, just like us. The next scene, Eagle Eye, a film from 2008 where a super intelligent computer is trying to take control over the world. People try to hide from it in a soundproof room. They turn off their devices, turn away from windows, but the artificial mind uses a camera to read their conversations from the vibrations of water. 2016, guys from Microsoft, Adobe, and MIT published a technology which is able to register micro vibrations from images at level of 100 degrees of a pixel. You cannot hear that, but that was the sound which was heard only by this flower. And this was actually a sound which was reconstructed by looking at this video. Yes, this is a video, if you don't notice, but the pixels are vibrating by 100th of a pixel, which is quite an amazing technology, isn't it? And this technology was developed by people from blood and bones, just like us. Finally, awaited by everyone in this room, David Hasselhoff and his talking car. It talks, well, that's not too extraordinary, but it knows what it is talking about, and it can describe this environment better than Eliza Orzeszkowa-Niemen. Fiction, 2015, a machine is able to semantically segment an image and generate grammatically correct sentence describing it. And all these images descriptions that you can see here were generated by the machine. Is it impressive? Well, if this is impressive, wait for the next one. Also, 2015, Generative adversarial network learns to draw photorealistic images based on what you say to it. Now, no one has ever made this photo. This bird does not exist at all, similarly to any of these. This is how a machine learned to imagine this sentence. That's quite amazing. And this technology was developed by people from blood and bones, just like us. Now, let's not forget that our car can actually drive itself. Impossible? Well, obviously, you know how much is going on in this field at the moment. And in TomTom, since 2015, self-driving car technologies are being developed extensively to enable cars to hit roads globally. And these technologies were developed by people from blood and bones, not like us, by us. We are quite proud of it. Here in our country, a chance? I don't think so. I could tell you who wrote these patents, but ladies and gentlemen, we didn't come here to boast. Okay, using similar technologies, robots can do their job on their own. Drones can fly, machines can see. We live in these amazing times where all the technologies are at our hand, and we can participate in their development. And let's start this amazing adventure by classifying cats and dogs. We won't do that, but I just couldn't help to scare you that we are actually going to deal with that. But anyway, before we talk over our recent challenge together with Błażej, let's first understand the fundamentals of convolutional neural network. And for start, let's do something basic, and let it be classifying faces into glass carriers and naked. And before we launch our artificial intelligence to solve it, let's think how we could solve it in a more traditional way. And let's think of a step-by-step solution. First, let's find edges by applying proper horizontal and vertical filters to the image. We do it by convolution or correlation, which is simply creating a mask and sliding it across the image and computing sum of products to all overlaying pixels. And that's the result. And having done that, let's look at a further scale and now design also a filter that would detect frames. They would obviously compose of vertical and horizontal edges, and after convolution, we could have frames detected. So again, we can look at this image at even farther scale and design a filter that would detect glasses. And finally, we can yet again zoom out, look at our image as a collection of individual pixels, and now create a simple classifier distinguishing naked from glasses. And as a result of matrix multiplication of these two, we will get some results which we can turn into probabilities by just applying function like softmax. A very nice framework that could help us to implement that is TensorFlow. Tensors are just multi-dimensional arrays, matrices, and that's what we have flowing for our graph of operations here. Our input is images, is a 4-dimensional tensor whose dimensions are number of images, in our case just one image here, dimensions of the image, here it is 200 by 180 pixels, and number of channels, this is a gray image, so it's 1. Our edge filters will be small filters like the one in the animation, which you can see, so 3 by 3, working on a 1-channel image, and we will have 4 of them. 2 vertical for left and right edge, and 2 horizontal for top and bottom edge. So the result of convolution is a 4-dimensional image of the same size as before, because we have 4 filters. Now, when we want to look at a further perspective, we can just resize our photo, but we would lose a lot of information if we do that about the edges which we detected, because with typical interpolation strategies, we just blur this image. So, and here when the edge was detected, we had very high value of the pixel, and we want to keep it. So instead of interpolating over the neighbors locally, we will choose the maximum value of a pixel, which is called max pooling. This is what we are doing here. So we max pooled our image by size of 10, and we will convolve it with 5x5 frame filter operating on 4-dimensional image. We have only one filter, so we get one channel output of the same size. Then we pool by 2, convolve with 6x6 one-channel glasses filter, only one, so we get one channel image at output. We pool it by 2 again, and then we flatten it to have 25 pixels and multiply by properly crafted mask, which would be 25 by 2. That's what we are going to do, and let's jump into TensorFlow to actually implement that. We are going to use TensorFlow, NumPy, OpenCV for visualization, and OS for paths. We will need to load images, and we have them in 2 folders, 0 folder for naked and 1 for the elite with the glasses. We take our folder, we will initialize our loader with that, and now we need a method to get a batch of images to work with as a tensor, and then we will prepare a class to return proper filters, detectors as tensors, which we'll specify later on, but now let's only predefine some arrays into this class, initialize with zeros, and let's have separate method for each of them. In TensorFlow, by the way, tensors have their own names, which is so sweet. So finally, we want to have a shower, to show tensors by name. It will need a TensorFlow session to find them by name, evaluate, and show them, because that's what the showers are meant to do. So now these should be quite straightforward to implement, not too important for our talk, so let's just implement them really quickly. Guys with laptops trying to keep up, please let me know if that is not too fast for you. Okay, we are done. So let's start to write our TensorFlow graph. We need a placeholder to feed our images to the graph. We know their shape, but we don't know how many we would need, hence the none here. Let's have a placeholder for the labels to our images so that we can later verify if the detector is right when we have it. And now let's take our input images and our edge filter and perform the convolution. It is a very simple operation, but let's use TensorFlow operation. We will slide our window with unit step and pad the result to have the same size as the input. And max pooling resizing is also implemented in TensorFlow, so let's just use it. We will resize k times the actual image dimensions, decreasing the dimensions. So we want padding to keep the same image size, set k to 5. And now let's just run the last node of our graph, feed the session placeholders by images loaded by the loader, set up some visualization, correct some bugs, and run the program in a second to realize that it's all black. It's obviously black because we didn't implement the edge filter, which we'll do now. So we design a simple 3x3 slope to detect right falling edge. And now we just transpose it, we flip it to have the other right edge, then transpose it to have a bottom edge, and flip and transpose to have a top edge. That's very easy. So now we'll see that how our program works. We see our 4 filters, which we have just designed from scratch, pixel by pixel, and although that was quite trivial, they do the job. We have the edges detected, and one obvious problem, which you can probably see here, is that we have 2 pairs of symmetric images, very similar to each other, which is not good. To build a multi-layer system, we need each filter to be responsible for what it does, to be very independent. So we can simply keep the positive values and put the negatives to 0, or using the vocabulary of the world of science, let pass it through the rectified linear unit. So in short, ReLU. TensorFlow has it, so we just use it, add the code to show it, and run the program. And as expected now, the left filter gets the left edges only, the right filter the right edges, and that's beautiful. Now, as we will repeat the conv pool ReLU block, let's extract that. We'll call it a layer. It will accept the input and the filter for convolving and max pooling size, and it will just return the result. Let's clean some mess, and we have our first detecting layer for detecting edges. So let's go with the second one. Okay, that we will detect now the frames. So let's detect our filter. That is quite easy. It should be a 5 by 5 image, like detecting like a square. So we do it. It's a 4-dimensional image with input from the previous layer. So it's quite easy. Let's run it. We can see our filter, and we can see that for the girl with glasses, the top one, we detect 2 small dots, and for the girl without, we detect nothing. So which is probably something that we would expect from such filter. These 2 dots, now we would like to detect them in the next layer. So we'll create the glasses detector, and it will be a 6 by 6 filter designed with just 2 dots detected somewhere in the middle. That's quite easy. Now, okay, we need some normalization of our result a little bit. We can do it also manually if we want it. That's not very important. And in a second, we will run a program, and we will see, yes, we'll see a 5 by 5 pixel result with a glowing pixel somewhere in the middle for the lady in glasses and an empty for the other one. So now, as expected, we will flatten this result to a 25 pixel vector. We can do it quite easily with resizing, and then we actually know its dimensions from the previous block. We can assign it dynamically. And now we will do the matrix multiplication of this result with our naked or glasses classifier. It will have 2 rows, which we design in a second. And in the first row, we can just put constant values because this is detecting nothing. And the second thing detects somewhere some high value in the middle. So we just do it, and we'll run it. There's a small bug here, but it doesn't matter. We have the result. It looks like this. We run the program for 4 persons now to get some more data to look at it. We still didn't find the bug, but we'll find it later. Just don't worry. We are doing quite fast, but don't worry. It's just to show you more or less the stuff, what is going on. And now let's write some metrics of what we are doing. We get probabilities straight by softmaxing output of the classifier. And we will calculate some accuracy, which is percentage of correct predictions, and we will calculate loss, which is how far we are from the correct answer for each case, and we will define cost, which is a mean loss here. And when we print the result, we will see that the cost is quite huge. We will correct our mistake. Now it's debugged, and now we will run it. And we can be happy because we can see in the console that the cost of this solution is 0, accuracy is 1. We have only 4 examples, but it's working perfectly for these 4. You can see in the pixels, the last layer of the pixels, you can see that for first 2, the second pixel is, so pixel at index 1 is very light, which means we have a class 1 glasses, and the last 2 images have more glowing left pixel, so the 0 index pixel means it's a class 0, so there is no glasses. So it's working very nice. We have 100% accuracy, 0 cost, wonderful. And when we run it for 8 people, we unfortunately realize that not all glasses look like windows. It's quite problematic. We are proud of our solution, but we would need probably to tune our filter coefficients a little bit to reduce this cost and make our classifier be more general. But instead of tuning it manually, we will instead, with just one line of code, will make the machine optimize it for us. This is very important because up to now we were doing some manual stuff, and now by staring at this line being typed, you are literally witnessing death of the handcrafted human algorithm and the birth of artificial intelligence. I can feel the thrills in the air. So let the optimizer run for 1,000 times over different batches of images and labels fed to the placeholder. And now, at every epoch, let's show some results, which we shown before. So let's just write it, yeah. Let's show these images at every epoch. So at every time, all of the samples are shown to the optimizer. Let's show only the filters for now. And okay, let's define some reasonable batch, divide the data into training and validation set. And at this point, your operating system might get a bit intimidated by the artificial intelligence, and probably it might ask you for an update. However, it should already realize that for some systems, there is really no hope. So what we do now is not very exciting. We are just setting up a message to be shown at every epoch to show how we are doing. You will later see the result. We'll show some training and validation accuracies and the cost. And when you run the program, we will see in the console that there is no variables to optimize, obviously, because we put our variables, our filters as constants. So we need to change them, and actually they will be typical variables with randomly initialized with the same shape as we had before. So we do it for all of the filters. And after doing some stuff, we run our program, but we forgot to shuffle the data set, so we just add it and create the functions to split the data sets into validation and training set, which we are quickly implementing now. And having done that, we run our program and we can see how the filters are beautifully evolving to actually become the detectors. And if you look at it closely, probably you will notice that they are very similar to the detectors that we manually created, because the first two are just left and right edge. If you look perfectly, it is a bit skewed. Then the third filter is just a top edge filter, which is very, very nice because we had a right intuition while we were creating these filters. That's really amazing. And we reached accuracy of, as you can see, about 85%, which is not very bad and not very good, but we can add some more freedom to the machine, but by a lot of things. For example, by enabling convolution to have the bias term. So we are doing this right now. We can make the max pooling a bit less aggressive. 10 was a big number, and now we change it to, we can add a few more filters. And now, when you run this, you can actually start seeing the performance beyond any handcrafted design. You can see formation of filters that you would not be able to come up, even it's so small. 90%, which is the result, is still a poor result, but you can obviously go a bit deeper by adding another layer, letting the machine to build its comprehension with more levels of detail. And with this relatively simple task of detecting glasses, non-glasses, and maybe by maybe just adding more layers, one or two, we could surely go to almost 100% of accuracy. But you can see our nightmare returns after 4 hours exactly. This is last time we set it to wait for 4 hours, so time goes really quickly here. So the question is deep learning then just about stacking more layers as the complexity of the problem rises? And not exactly, because every layer comes with responsibility and risk. And deep networks are hard to train because they are trained by backpropagation, and the gradient can become unstable. It can vanish, for example, and then the early layers will train extremely slowly or not at all, or it can just explode. And as this field of science evolves, the new ways to solve these problems arise from traditional techniques like smart initialization of weights, regularization, gradient clipping, new activation functions, up to solutions that are so clever that you actually get thrills when you read a scientific paper. For example, GoogleNet was so deep that it could not be trained by standard optimization of the loss at the end. So for the first time, to make these earlier layers actually learn, auxiliary small networks were attached in between the layers, designed in such a way so that they all learn the same thing and the cost is shared. Amazing idea. Microsoft, in their ultra-deep network, introduced residual connections so that the successive features are put in the context of the previous layers, and there is additional path for the gradient to backpropagate. That's an amazing idea, and we could talk hours about various beautiful solutions emerging every day in this field. The best news is that there are plenty of resources, training sets, state-of-the-art architectures, all available for you to examine, download from the web, and reuse. And how to be successful in this everyday practice, Błażej will tell you about it now by walking you through one of our recent projects.
Hello? Hello? Hello?
Or not.
Hello? 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 Oh, now it's working. Hello, everyone. Now we are going to show you our exciting project. So, no worries. We want to classify dogs and cats, and I'm not showing this picture to repeat a joke of Chris, but to be honest, most of the AI problems are quite related to very simple tasks like classification, and very really similar to classifying dogs and cats. But today we'll show something else. We'll show not really typical usage of deep neural networks. So imagine that you are watching some movie, and there are a lot of faces, a lot of characters, but in fact, you are interested only in one actor, and you would like to find all the scenes where Chuck Norris appears. So, can we think, how could we find Chuck Norris in our movie? Could we turn this task into a classification problem? Of course, yes. We could gather a big data set collect 1,000 or at least a few hundreds of pictures of Chuck Norris and maybe other characters to have a second class for our classification problem. But actually, it would be quite difficult and quite a big effort to collect such a big data set, and it doesn't look like a reasonable solution. Yeah, we would have to train our own network. If we want to find another character, we would have to retrain our network. So it's not generic thing. Yeah. So let's think what is our task. Our task is for any two randomly selected faces to say if they are the same or they are different. So if they belong to a different person or belong to the same person. And of course, we need some algorithm or other pieces of machinery to accomplish this task. In fact, there is class of deep neural network specialized for this type of task, and that can solve such a problem. And when we feed this kind of network, this kind of network produces a feature vector that is called phase embedding, and this kind of feature vector should meet some criteria. So when we feed the network with another phase of another person, Euclidean distance between these two vectors should be quite big. But if we feed the network with the phase of the same person, Euclidean distance should be very small. So the question is how to train such strange network. In classical network, we have loss function like this. So we minimize the error between expected label and actual real output of our network. But in our case, we don't have labels. That's why, yes, in this case, we want to minimize the margin between vectors from faces of the same person and maximize the margin between vectors from different persons. And for that, we use a special loss function, which is called triplet function. And while training such a network, we don't feed network with only one image, but we feed it with 3 different images, calculate 3 different feature vectors, and calculate loss equation. In fact, it is quite, yes, we see that there are 2 blocks for B minus C, which is minimized, and A minus B is maximized because there is minus between this block. In fact, it's quite difficult to train such a network. It is complicated. But if you want to dive into details, there are nice papers to read about that. But today I want to show something simpler, something that everyone can try at home with not a big effort. So we'll use something that already exists, and we would like to add something on top of that. We'll use deep neural network trained for face recognition, but we'll remove classification part. So at the end of the network, we have just feature vector. So when we feed the network with 2 randomly selected faces, we have 2 feature vectors. These vectors come from the network that are trained for face recognition. So for sure, they contains information about important face features. However, it doesn't come from the network that was trained to margin distance between these vectors. So we cannot then compare them easily with Euclidean distance. That's why we would do something different. We subtract them and we train our own very small, very tiny, fully connected neural network to classify if these 2 vectors belongs to the same person or to the other. To train our new network, we need some data set. We used well-known data set called labeled faces in the wild. It contains a few thousands of people. More than 1,500 people have more than one picture. And when we are using this data set, we select randomly the picture of some character, choose another picture of the same character, and we feed the network, and we set the expected label as 1 because this is the same person. On the other hand, when we want to show negative example, we set expected value to 0. Of course, to train network properly, we need to present positive and negative examples uniformly. And let's see how it works in the code. To make things easy, I used Keras framework, which is in fact a wrapper over TensorFlow and other frameworks. And if you ever think about spending a few minutes with machine learning, I think Keras is really right choice because in just a few lines of code, you may have a piece of working network. In our case, we have a very small network with just 3 layers. We just set activation function size of the layer and just that. We use Adam optimizer, which is commonly used for training networks. We have to compile our model. It is in Keras. It is always called after defining the model. We call function compile when we set what is the loss function. Binary cross entropy is typical loss function for classification problems. And we also can add some metrics that will be stored in historical object that can be shown on the screen or whatever. And also we set Adam optimizer here. And then we can run the training model. We use feed generator version of training function, which accepts Python generator that prepare batches of training data. And now let's see. Now let's see how it really works. So it's time for demo. So it's time to crash something. So now we will run training the network. Okay, I don't see the screen, so it's starting. It is very convenient that Keras provide all this reporting out of the box, so you don't have to do anything, just run fitting and it's just working. Because behind there is TensorFlow, I also added callback to prepare TensorFlow logs. So I can use a very nice tool which is called TensorBoard from TensorFlow for showing logs, to showing accuracy. So I have to run TensorBoard with log directory. Okay, it should working now. So now I have to. Oh, where's my? Where's mouse? Okay, it's working. So it is the curve of accuracy. In fact, it's training accuracy. We can also scroll down. There is also places for validation dataset accuracy. It is not very smooth. I reduced the size of validation set to be able to run this at this demo. So it is not really smooth. Let's see also validation loss. And let's come back to the training. We'll see. Oh, not this one. So Sorry. Is it still working? Yes, there is one more epoch. Tensor board is very powerful tool. If you add other logs to your in your application, you can also show other metrics, not only accuracy, but whatever you want. Okay, it finished. Now we are going to run our network that was trained here. Yeah, here. So I have web camera, and I will try to run it with real data from camera. We'll see if our network is really working. Whoa, what is... Let's try again. Oh, yeah. So we will look for this guy. Okay. Here's the video from our camera. Let's see if this is me. Not really. Okay, let's see if this guy. Oh yeah, this is this guy. It's not perfect sometimes because of noise of the camera. It shows wrong probability, but it works quite nicely. Okay, now it's time for conclusion, so we come back to the presentation. Wow.
Okay. Do you know what that is? I will tell you. The top cross is what the person is looking at the moment, and the cross below is what the machine generated by analyzing their brain activity. And these are other examples. And to me, it's quite amazing, but it's also a little bit disturbing. Maybe it is not a fully deserved reading in your mind, but that's clearly a first step, already tested and documented in the literature. So soon, the machine will be able to read your mind. It is going to learn any task you give to it. And it will always do so by optimizing the cost, optimizing the objective function. So whether you are designing it for saving the planet or winning a board game, please make sure to double check two things. First is to set the cost of human life to infinity. And the second is check if the infinity is properly implemented in your environment. That's all. Thank you very much. Any questions?
Hi, thank you for the amazing amazing presentation. So, how long does it usually take to train a neural network that can be applied to real life? Like not a demo.
Okay, it really depends on how you approach the problem and how deep, how complicated is the problem you're solving. Because it might take weeks. For example, if you have a very complicated problem and use a very deep network for that. As you can saw, my example of detecting glasses, non-glasses person was like maybe 1 hour on a CPU or even less. We could now, what we did here, we could train our network very quickly on the GPU while you were seeing it, but the approach we had was actually we used already trained embeddings and then only train a small network over what we trained before. So there's transfer learning, which makes your training quite fast because you are not training everything from scratch because someone already pre-trained that. That's short. It might be sometimes, depending on the project, from an hour to 1 or 2 days. But if you do it from scratch on the new problems, then it's quite intensive and long.
Compared to analyzing video or images, how hard it is to train a neural network to analyze text?
Text?
Mm-hmm.
Well, again, it depends on...
Can you use TensorFlow for that?
We can use TensorFlow for that, of course. Do you want to approach this question? It's very hard to say. It really depends on what is your input. In image analysis, your input is a tensor of images, let's say. And if you are doing the word analysis, they may be word embeddings. There's a lot of possibilities, and it depends how complicated the problem is. Again, usually the problems in text are a bit less complicated, but it's not a rule. Because what generally our site is really intensive. There's so many things to understand. So it usually takes a bit longer, but it really depends on the project. It's very project specific.
Maybe I didn't catch it correctly, but the network you were using was pre-trained. You just stripped out the last output layers, and then you used your images to classify if the image you put in is similar to one colleague or the other colleague. Is it general now? So you can use my image and say
Yes.
it is me on the camera?
Yes.
Yes.
Okay, thank you.
We could try it, but maybe not now. But you can come later. We'll take a photo of you, and then we'll try to find you. We need just one image of this person to find it in the room.
Is this project of yours available on GitHub or somewhere to use?
Which one?
The last
No,
one,
it's
with
not.
the one that you demoed.
No, it's not available. It's probably still a little bit too ugly to. maybe we're not sure yet. Yes, we just in fact we were still implementing it yesterday. So. Thank you very much. Then.
Thank you.